the equation that made certainty impossible. For centuries, humanity believed the universe followed clean, predictable rules. That belief shattered the moment one equation refused to behave. To understand why certainty collapsed, we need to return to a time when mathematics promised absolute truth. Equations were seen as perfect machines. Feed them numbers, and they would deliver certainty every time. This promise shaped science, engineering, and even how people understood reality itself. And for a while, it worked. Bridges stood. Planets followed their paths. Predictions came true. But beneath that confidence, a quiet problem was forming. Mathematicians began pushing equations into new territory, trying to describe motion, change, and the infinite with greater precision. They wanted formulas that could explain not just where things were, but how they evolved moment by moment. The goal was control through understanding. At first, the equations delivered exactly what was expected. They described smooth curves, stable systems, and predictable outcomes. Small changes led to small differences. Cause and effect felt reliable. The world looked tame, even elegant, when written in mathematical language. Then came an equation that behaved differently. It looked harmless, simple, almost ordinary. But when mathematicians adjusted its inputs by the smallest possible amount, the results exploded into wildly different outcomes. Tiny changes didn't stay tiny. They multiplied. They spiraled. They erased certainty entirely. This wasn't a mistake or a flaw in calculation. The equation was correct. The math was sound. The instability was real. And it suggested something deeply unsettling. That even perfect knowledge of the present might not guarantee knowledge of the future. At first, this idea was ignored. It contradicted centuries of mathematical confidence. Surely, with better tools and sharper methods, certainty could be restored. But every attempt to tame the equation only revealed the same truth again. Precision had limits. Prediction had boundaries. Quietly, without headlines or alarms, mathematics crossed a line. It stopped being a source of guaranteed answers and became a mirror reflecting uncertainty itself. And once that door opened, it could never be closed again. The equation's strange behavior refused to stay contained. As mathematicians studied it more closely, they noticed a disturbing pattern. The further they extended the calculation, the faster certainty dissolved. Each step forward multiplied the uncertainty behind it. Prediction did not slowly fade. It collapsed. This was not randomness in the ordinary sense. The system followed strict rules. Every step obeyed the equation perfectly, yet the outcome looked chaotic, unpredictable, almost alive. Two starting points, separated by a microscopic difference, drifted apart until they described entirely different futures. The math was deterministic, but the results felt uncontrollable. This discovery challenged a belief that had guided science for generations. If the rules were known and the starting conditions were precise, the future should be predictable. That assumption powered physics, engineering, and even philosophy. But this equation suggested a flaw in that logic. Knowledge alone was not enough. As researchers explored further, they realized the problem was not the equation itself. It was sensitivity. The system reacted so strongly to initial conditions that no measurement could ever be precise enough. There would always be an invisible error, and that error would grow faster than any correction could contain it. What made this realization more unsettling was how ordinary the equation appeared. It did not require extreme values or exotic mathematics. It emerged from simple relationships, the kind found in population growth, weather patterns, and physical motion. The instability was not rare. It was woven into everyday systems. Slowly, the implication became impossible to ignore. If such behavior existed in one equation, it could exist in many others. Predictability might not be the default state of the universe. It might be the exception. Mathematics had not discovered chaos by accident. It had uncovered a boundary where certainty stopped working. And beyond that boundary, the future became something that could be modeled, but never fully known. As this idea spread, its consequences became impossible to contain. If equations could obey every rule and still defy prediction, then certainty itself was an illusion built on fragile ground. What mathematicians once treated as noise or error was suddenly revealed as something fundamental. This shift forced a re-examination of systems once believed to be stable. Weather models, for example, relied on equations similar in spirit. Small errors in temperature or pressure readings were assumed to be manageable. But under this new lens, those errors were not minor. They were seeds. Given enough time, they could grow into completely different outcomes. Forecasts did not fail because the math was wrong. They failed because precision had limits. The same pattern appeared elsewhere. In biology, population models showed sudden swings that no average could smooth out. In engineering, feedback systems revealed thresholds where stability vanished without warning. Even simple mechanical systems, when pushed far enough, slipped into unpredictable motion. The world was filled with systems balanced on invisible edges. This realization created a quiet conflict at the heart of mathematics. The discipline had always pursued certainty. Proofs were absolute. Results were final. Yet here was a framework where correct equations produced futures that could not be pinned down. Mathematics could describe the rules of the system, but not its long-term behavior. Some resisted this conclusion. They argued that better instruments and more computing power would eventually restore predictability. But simulations told a different story. Increasing precision only delayed the breakdown. It never eliminated it. The divergence always returned, sharper and faster. What emerged was a new understanding of complexity. Order and disorder were no longer opposites. They were intertwined. A system could be completely lawful and still behave unpredictably. Determinism and uncertainty were not enemies. They were partners. This was the true conflict, not between chaos and order, but between humanity's desire for certainty and the universe's refusal to provide it. The breaking point arrived when mathematicians stopped trying to eliminate uncertainty and instead began studying it directly. What they found was not failure, but structure. Hidden inside the unpredictability were patterns, limits, and shapes that repeated across systems. Chaos was not random. It had rules of its own. This realization changed everything. Instead of asking for exact predictions, mathematics learned to describe ranges, behaviors, and tendencies. It became possible to say how unstable a system was, how fast uncertainty would grow, and where control would inevitably be lost. Certainty did not disappear. It evolved. The equation that once shattered confidence became a tool for understanding the real world. It explained why weather forecasts break down after days, why markets swing without warning, and why small decisions can reshape entire outcomes. The future was no longer a straight line. It was a branching path. In the end, mathematics did not fail humanity. It revealed a deeper truth. The universe is not a machine that can be perfectly predicted. It is a system sensitive to every touch, every fluctuation, every hidden detail. And within that sensitivity lies both danger and possibility. Today, this understanding shapes how we model climate, design technology, and manage risk. We no longer seek absolute certainty. We seek resilience. We prepare for change instead of denying it. Sometimes, the smallest shift in perspective becomes the beginning of a new future.